everyone, I'm Yogini Ma'am, Data Science Trainer at SevenMentor. Last session we saw about the statics. What is statics? Why is it important? Also we saw the descriptive statistics. We saw the concepts like central tendency, dispersion, position, correlation, etc. Today we will be moving forward with inferential statistics. Inferential statistics mainly deals with the probability concept. So let's start with the secret power of probability in data science. So today's agenda will be inferential statistics, random variable, probability distribution functions, hypothesis testing, and A/B testing. Okay, so we will be going in detail with all these concepts. Let me first introduce the inferential statistics. Last time we saw what exactly the descriptive statistics does and inferential statistics does. Descriptive only analyzes, it doesn't predict. Okay, descriptive only analyzes, it only analyzes. Inferential, it predicts. On the basis of previous analysis, that is on descriptive statics. So the concepts which are usually used in inferential, or we can reframe it, inferential statistics depends on these terms: population, sample, estimation, hypothesis testing. So population is the entire group. Okay, it is the entire group. Sample, it is the subset of population. It is connected with the sampling technique, the process of selecting a subset. Selecting a sample from the population, this is called the sampling technique. You can remember in this simple language. Okay. Estimation, what is estimation? It is the unknown it has unknown population parameters, mean, proportion, variance, by using the sample data. See, estimation and hypothesis, whenever we deal in inferential statistics, we always go initially with the sample data. Last time, as I told you, we can't go with the whole population. We need to take a bunch or a handful of sample, it depends upon the scenario, and then we have to do the testing, the predictions, whatever the test or whatever the outcome you want, you always do it on the sample data, not on the population, because it is very cost effective. It increases the model size also, and we are not sure whether we are going to get the correct outcomes. Coming back here, estimation. I would like to give you an example. Like, we know that average score of the students, it is based on the sample. Also, if you take a bowl of soup, you don't drink completely. That is not called as tasting the soup, right? You just taste a spoonful, right? Only a spoon you take and you say, yeah, the soup is nice, or the soup is sour, the soup is sweet. You conclude accordingly. So that is nothing but estimation. We can say that it is an estimation. The next very trending and very interesting, very favorite topic of all the interviewers, hypothesis testing. Testing claims or assumptions about population parameters using sample evidence. In hypothesis testing, we first initially make a statement and then try to find evidence for it. If we get, then we don't reject that statement, and if we don't get any kind of evidence, we reject the whatever statement we have said. Okay, so one very important point estimation, it is the starting guess. See, we can say whenever we deal with a data set, okay, we can make a starting guess. Maybe the mean is around this, the mean of population maybe around this value. Let's consider it is 50. Okay, but confidence interval, it will give a range of population mean. Okay, so we will be seeing in next slides. Okay, yes, estimation, as I told you that it is just a point. It may be a point or a range. Okay, so single value that estimates a population. Before this slide, we saw that the average height of student, it will be some value, let's say 163 in a class. Okay, so it estimates mean, sample mean estimates population mean. We can say in a simple technical language. So instead of taking all 50 or 60 height of each and every child in a class, we can just take a handful or just say 10 to 15 students' height, and then we can conclude that yes, the average height is 163. Okay. What is confidence interval? What is interval estimation then? Why this concept came into the picture? See, if I go in class A, I will get 163 as the average height. If another teacher goes in the same class, she may get 158 because the samples are different, right? The same student won't be in her estimation, right? So another one more sir comes, he takes 160 as the, he gets the average height as 160. So just tell me, at this point, is point estimation the correct parameter? No. So we can't say no, 163 is the correct estimation which we have given. So in this case, the confidence interval comes into the picture. It is very interesting. I'll tell you. See, as you can see here, these are the values which we got as an average. So now I can tell that my range of average height starts from 158 till 163. Correct? So the population mean may lie in any of them, can lie in between 158 to 163. Let any other professor come or let any other person come and check the average height. Clear? So this average height, this range is known as confidence interval. Why the name confidence is given? Can you think? Yes, we are confident that I am damn sure you pick up any child from the class and measure the height. The value will be between these only. Okay, we are not going to consider the outliers in this case. Okay, those are the exceptions. Okay, so we are much confidence. But can you give the same confidence in this? No, we can't. Correct? It may change, right? Okay, so this was the example to understand. Okay, also I would like to just correlate standard normal distribution here. 95% of data falls in this confidence interval. Just remember this thing, we will be covering it in standard normal distribution. Okay, so like this. This is my confidence interval. Clear? Okay. Next parameter comes hypothesis testing. Okay, now I know the confidence interval or I know the point estimation. It depends upon the data set which you have. Okay, so we will do some test to understand what our predictions or our data set are likely to give the outcome. So for that purpose, we use parametric test and non-parametric test. we will be seeing in detail. Okay, so let's start with the beautiful topic, random variable. What is random variable? Random variable assigns real number to each outcome in your random experiment. Okay, it will give something or the other value for your outcome. So it is divided into two parts, discrete and continuous. Discrete value, as I told in the last lecture also, it mostly deals or it only deals with integers or the whole numbers. The continuous values, it deals with your decimals. Okay, these deal with the decimals. Clear? So here the technical definition of discrete distribution is, discrete variable is finite and countably infinite numbers. The function associated is probability mass function. Continuous, it will take infinite number of values and the function associated is probability density function. Just remember these concepts because going forward you will be understanding how these discrete and continuous are important. Okay, see, as the variable is there, the functions will be accordingly, the distribution will be accordingly, and the test for them will be conducted accordingly. They are both different. Okay, so discrete and continuous, we will be having different functions, different distributions and different test terms. Yes, so let's see what is probability distribution function. We know what is the definition of probability, the outcome, right? The outcome of an event, of a function, etc. Okay, so what is probability? We know what is probability. It is the outcome. Okay, it is the outcome which we will be getting depend upon the event or the scenario or the data set which we are going to get. So we do have its distribution, how it will be distributed, how our data set will look like. So this is probability distribution. We have some functions related to it so that we can analyze the data set or we can analyze the event accordingly. Okay, so it shows different outcomes for a random variable. It is mathematical way of showing how different outcomes are in random event. Okay, this we all are talking about only the sample data. We don't check it for population. Okay, so it gives probability of each possible result and addition of all the possibilities is 1. Let's say for a model, I give an input, some input, and it is to be asked, predict whether it is a dog or a cat. Just predict what image is in the output. So the probability of dog is 0.8. Then the probability of cat will be 0.2. Why? Because of this. All the probabilities have the addition as 1. Okay. So here you can see the addition is 0.8 plus 0.2. It comes to be 1. Clear? So let how many be the outcomes, number of outcomes, n number of outcomes, but the addition will always be 1. Yes, we saw this. The functions associated with discrete is mass probability mass function, continuous function, continuous functions it has probability density function. These tools, probability mass function and probability density function, help us to analyze data, predict trends and access risk. Okay, these trends we will be able to see in time series. Okay, these are the images which show you the different, what you can say, the distributions of random variables. Okay, this one and this one. Yes, this is the classification or the tree diagram of probability. Just learn this, okay, just learn this. This is very easy to understand. Once you are good with this, you will be able to understand why we need to analyze a random variable, what is the importance and how to do it. Okay, so let's start. Discrete, continuous, discrete distribution and continuous distribution. In discrete we have uniform, Bernoulli, Poisson and binomial. These all four types come under discrete. Okay, for continuous it's normal, standard normal. Yes, just before I said you that we have the confidence interval 95% in standard normal distribution, so I was talking about this. Okay, T distribution, also known as student's T distribution, and chi-square. Okay, let's start one by one. Discrete functions. So as we know now what discrete value or discrete random variable or discrete function will give us, what kind of values they will be having. They are countable distinct values. Each possible value has a certain possible assigned to it. See, just now I gave you the example of dog and cat. Correct. If dog has 0.8, some or the other value is assigned to this cat. It is not like that. Yes, dog is getting 0.8 and it is near to 1. So we will be just getting the probability of dog. No, it will be giving the probability as 0.2. Some or the other probability will be assigned to this cat. Okay, cat value or any other outcome which we are going to get. So we have to fulfill what we need to fulfill, the condition, the theory that addition should be 1, right? Yes. So examples, tossing of 3 coins. Okay, students absent in a single day, rolling of a dice. Absent student, can it be 4.5? No. 10.5? No. It sounds something weird, right? And illogical. A small child will also tell what you're telling, that it is 4.5 students absent. No. So that's the reason these are giving us whole numbers and integers, so they fall under discrete functions. Clear? Okay. Uniform distribution. It gives you the first is uniform distribution. It gives you the equally likely possible outcomes. I won't say event, it is giving the outcome, right? It is giving the outcome of the event itself. Okay, so example of dice, it will give 6 possible events, or it will say no, I'll give only 3 possible events and other 3 I'll give half of. It is not possible, right? Illogical. See, inferential, probability, everything mostly depends on your logic. Whatever logic is there, it should be applied in theory. Okay, simple to remember. So interesting, right? So logic we use and we apply in our day-to-day lives also. So like rolling of a dice, 6 possible events it will give, right? No bias, single outcome, because it will not say, if I just roll a dice, it will just give 2? No, because it is not biased. Okay, it will give only 6? No, it won't. It will give equal importance. See, the meaning of this sentence means equally likely, means everyone is getting equal importance. All 1, 2, 3, 4, 5, 6. Everyone is getting equal importance. Okay, so it is not like that I'm just rolling it 4 times, so I'll get 4. Okay, the dice is not biased. It can be visualized as straight horizontal line. Okay, straight horizontal. See, I have just purposefully given this diagram so that you can imagine how the outcome will be there. Okay, visualization helps more, correct? Okay, so it resembles rectangle rather than normal bell distribution. Okay, see, whenever we are like used to such distribution. Okay, this is bell curved. Okay, this is bell curved. Instead of getting bell curved, we get a rectangular distribution in case of uniform distribution. Okay. Yes. The area that is covered, it is equal to 1. Okay. It is equal to 1. Deck of cards, rolling of a dice, tossing of a coin. Can we say, no, I can get the outcome of a tossing of a coin, half of the heads and half of the tails? No. Once you toss the coin, you will either get completely head or you will get either completely the tail, right? So that also comes under uniform distribution. Bernoulli distribution. Bernoulli distribution, it gives only two outcomes: failure or success, pass or fail. Clear? Like this. So in event where only two outcomes are possible, there Bernoulli distribution can be applied or Bernoulli trials can be applied. Okay. So the technical definition, just we'll have a look. Two possible outcomes are success or failure. Okay. It is the probability distribution for series of Bernoulli. Bernoulli, it is only for one experiment. For example, let's consider tossing of a coin. Okay, tossing of a coin. So, tossing of a coin, if I toss it only once, yes, that would be considered under Bernoulli distribution. If I toss it twice, then it won't be under Bernoulli distribution. Okay, I'll tell you where it will fall. Okay, so only once the experiment is conducted, then it comes under Bernoulli distribution. Okay, so here we can see Bernoulli distribution is a special case of binomial distribution. That is what I wanted to tell, that if the experiment is conducted more than once, it will be falling under binomial distribution. Okay. Number of trials that are conducted by Bernoulli trials that belong to binomial distribution, we can say in this way. Okay. So, example of Bernoulli distribution: flipping of a coin only once, pass or fail in any of the exam. Okay. So, that will be also once, lose or win any match or any competition, that will be also once. That will all fall under Bernoulli distribution. Okay. Yes, binomial distribution. As we have just seen Bernoulli trials, Bernoulli distributions. So, number of Bernoulli trials, it will lead to binomial distribution. Okay, binomial distribution. So here what we will be doing, we will be conducting the experiments. We will be conducting the experiments more than once, so that we can have a conclusion or we can understand how the event will be occurring in different situations, or would it be just same in all situations. Okay, that we will come to know. Okay. Yes, here important two parameters, number of success and number of attempts. Okay, it summarizes number of trials and observations. Okay, let's say I toss a coin 100 times. I toss a coin 100 times. So there is a probability of getting at least 40 times as head. Correct? Right. So 40 is my outcome, is my number of success. Okay. And divided by 100. These are my total number of experiments conducted. Total number of experiments conducted. So, okay. Clear with example? So these are the important terms. If anyone is missing, the other is of no use. Clear? Okay, so determines probability of observing specific number of success outcomes in a specified number of trials. The same I have just explained you using this. Okay. Yes. So number of success is given by X and number of attempts is given by N. Clear? Okay. This can be used in finance, banking, social science, etc. Also, we can check whether borrower will default on a loan or whether the company will miss it, the earnings. Okay. Poisson distribution. Poisson distribution, it gives you the discrete distribution. Yes, it falls under the discrete distribution function. So it will be giving you the calculations that are likelihood of certain number of events happening in fixed time interval. Okay, assuming events occur independently. See, this is the technical definition. Okay, I'll explain you here. Let's suppose I'll directly explain you the example. Here, otherwise I'll just tell you. Here, the probability of occurring of an event or getting the outcome is very less. Very, very less. And number of experiments means N is large number. Okay, it is large number. So here the Poisson distribution is there. We consider Poisson distribution. Okay, so now let's see the theoretical things. Okay, example, number of printing mistakes per pages. You might get only a single mistake, or rather you may get only 2 to 3 mistakes in your books, in your school books in that time, right? The answers of some mathematical sums, there was some printing mistake. So the whole book, let's suppose it is of 500 pages and you will get only a single mistake. So the probability of getting a mistake in 500 pages book is very low. Okay, in that case, the probability distribution is there. So it is characterized by a single parameter lambda that represents events average occurrence rate in an interval. Distribution is used when events are rare. Okay, number of occurrences in non-negative and can take integer values. These are just the concepts which are related to the Poisson distribution. But these are the technical concepts. But just try to remember in what case the Poisson distribution will be used, how it will be useful for us. Okay, where the events or the outcome is very less and the experiments are very high. Okay, so N is the experiment. Okay, N is the experiment. Also, another example we can see, probability of defective items in manufacturing company. In a larger manufacturing company, there is the chance of getting very less defective piece. Okay, fine. So next, continuous functions. Till now we saw discrete functions, uniform distribution, Poisson distribution, and what else we were able to see? Bernoulli and binomial. These all come under discrete functions. Just a small recap. Okay, yes, let's continue with continuous functions. Okay, as discussed, this will be dealing with decimal values. As soon as I say decimal values, you can just see weight, height. Okay, these can be in decimal, either 65 or 65.8, etc. whatever. Okay, so it gives a range, value within a range rather than the specific separate values. This separate values within the range, within range means it is the decimal values, and separate values means it is discrete values. Okay, yes. In ML, this continuous distribution plays a vital role, very important role, just to understand the uncertainty by showing how likely different values are to occur. Okay, how likely these values are to occur. We will be seeing this in the machine learning models in we can see it in linear regression, like how the data set is there, different columns, we will be able to relate it. Okay. Yes, it describes event that can take on a finite value, on any value within specific range, same decimal values. Okay. Yes, the importance of distribution. Modeling uncertainty. See, instead of giving some specific values, it gives the probability. Probabilities are in decimals, right? 0.6, 0.4, etc. Gaussian distribution. Gaussian distribution, it uses Gaussian distribution, the Bayesian. Yes, the Bayesian networks use to detect the errors. Gaussian distribution and Bayesian networks. Yes, the models use continuous distribution functions to get the maximum likelihood, maximum outcome of the respective likelihood estimation. Okay, so it will be dealing with different models in ML. Okay. Bayesian inference, it will be telling us that what the beliefs, okay, that we have made are correct. The beliefs about the parameters, relating to the parameters that we are going to deal, it is going to help in the Bayesian inference. Okay, Bayesian. Generative models, yes, it is also helpful in generative models. Generative models like variational autoencoder. Okay, variational autoencoder and Gaussian mixture. Okay, variational autoencoder and Gaussian mixture, they learn or generate data. Okay, they learn, and generate data. Both they can do with the help of continuous distribution functions. Okay, yes. So the types, we are starting with continuous distribution, normal distribution. This is widely used in most of the data sets. Okay, so it is commonly discussed and often found in real world. Real world data mostly uses this normal distribution. Okay, many continuous distribution often reach normal distribution. Most of them reach to the normal distribution. Normal distribution deals with mean and deviation. Okay, it has the value of mean and deviation. Properties that it has the highest probability and all other. I'll just draw the diagram here for you. Okay, so here it is. Let's suppose this is the mean. Okay, I'll just note it, mean, and maximum data, it is symmetric around the mean. Okay, it is symmetric on either side of its mean. Okay, both the sides. Yes, I would like to introduce the standard normal distribution here itself, because it is the special case of normal distribution. It is the special case of normal distribution. What is the special about standard normal distribution? The mean here is 0 and standard deviation is 1. You remember in last session we took mean we calculated. I'll just draw here and show you. Some marks were there like 75, 85, 65. Yes, in Z score. Yes, I was able to recall it. 95 and 55. Okay. So this is normal distribution. Then you remember we converted it into standard normal distribution where mu was 0. Yes. Okay. So here it is -1, +1, +2, -2. Clear? So these values are converted to standard normal distribution. Okay. So the same thing is here. We just implemented there first practically and then we came to the theoretical part. Okay. Yes. It follows empirical formula. What is empirical formula? It gives 68% of values. I'll just erase this diagram and I'll explain you properly. Okay. this is our normal distribution. I am telling you about standard normal distribution. Okay, so this is our mean. Okay, so this will be 68% data around the mean, means this is -1 plus 1, so this is 1 standard deviation. Okay, so -2 to +2, this is, I'll just give some other color like this, other design. Okay, so -2 to +2, 2 standard deviation. Okay, 2 standard deviation. How much data falls here? It is 95%. You remember just now in confidence interval, I told you I'll be introducing this concept. So most of the data or the population mean, it falls in between 95% of the data or standard deviation, in 2 standard deviation away from the mean. Okay, we can say in this way also. So 2 standard deviation, then this is -3 to +3. Okay, so the data will fall here. I'll just do one thing. I'll just remember here, I'll draw a nice diagram in next standard normal distribution. Okay, so the data falling between 3 standard deviation away from mean is 99.7%. Okay, yes. Okay, it is used in hypothesis testing. We will see how it is used. Okay, yes. So T distribution, it is also known as student's T distribution. It is similar to normal distribution. Only difference is that the tails of the distribution are thicker. I'll try to draw it. I'll use another color. So, sorry. Okay. Blue color. Okay. So, I'll just okay. See, this is our normal distribution. Okay, and this is the T distribution. Okay, I'll explain with this. Okay, so can you see, it is very thin, but these are so thick, correct? These are so thick tails. So this is similar to normal distribution, only the tails are thick. Okay, it used when sample size is small and proportional variance is not known. Okay, so in the case where proportional variance is not known, in that case T distribution is used, and we can say that sample size, okay, sample size is very small, sample size is small. Okay, and population variance, population deviation is not known in this case. Okay, yes, it is defined by the degrees of, freedom, which is calculated by this, okay, n-1. As the sample size increases, degrees of freedom increases. This is important concept. Okay, I'll just tell you in further points. The T distribution approaches normal distribution. What is the ultimate aim? To get the normal distribution. So if we increase the sample size, then the degree of freedom will also increase, and then we will be getting the normal distribution. Okay, we will be getting the normal distribution. So the tails will become more thinner. Okay, and the curve gets closer to mean. See, here we can see, this is our mean, the curve is more closer, this curve is wider. Okay, yes, the important point which I wanted to tell you, degree of freedom, I'll highlight this. Okay, with red color I'll highlight. Degree of freedom, very important point. Okay, degree of freedom. How we will get the thinner, thinner tails, and how we will get a normal distribution, the curve, how it will get closer to mean is degree of freedom represents number of independent features. These independent features are introduced in machine learning models. So their independent features are nothing but x. So x will be from x1 to x infinity. Like we have multiple columns while building the models. Okay, input, there will be multiple inputs. Okay, so in that case, degree of freedom represent number of independent features in data set. Okay, so if degree of freedom is increased, t distribution approaches the shape of standard normal distribution. Okay, if degree of freedom is increased, how it will be increased? Just now we saw here. It depends upon the sample size. So we need to increase the sample size in that case. Okay, yes. Chi-square distribution. It is equal to squares of p normal random variables. Okay, p, that is number of degree of freedom. Just now we saw it in t distribution. Okay, it is similar to like t distribution, it also has degree of freedom. Increase the distribution gradually approaches normal distribution. See here, we can see in this image, we can see here. Okay, now it will give you the the chi-square distribution. See, it is almost similar, or it is almost likely like your normal distribution. Okay, it is highly used in hypothesis testing to draw inferences about the population variance of normal distribution. Okay, this is the chi-square test. Okay, that is used in hypothesis testing. Yes, the favorite standard normal distribution. This is the favorite topic of the interviewers. What is normal distribution? What is standard normal distribution? So don't get confused. Okay, so don't get at all confused. Normal distribution, it is like this. Here your mean or mu, it is some value. Okay, and your deviation, it will also have some value. But in standard normal distribution, mean is 1 and standard deviation is 1. Sorry, mean is 0 and standard deviation is 1. So this is only the change, and we can change the distribution from normal to standard normal distribution. Okay, and then work on it. Okay, so this is special case of normal distribution. Bell shaped and symmetric. Here you can see it is bell shaped and the data is symmetric. Okay, so we here we have the drawing. It extends from minus infinity to plus infinity but never touches the axis. It never touches the axis. Okay, here you may assume that it is touching, but it won't touch the axis. This is called standardization. This is called standardization. The most interviewer favorite question. What is standardization? What is normalization? Normal distribution, normalization. Standard distribution, standardization. The process here is this of standardization. Okay, yes, it allows us to use same standard normal table for all normal distributions. These properties we have already seen. Symmetric around 0, the total curve is under 1, area is between minus z to plus z, represents probability, and that is uses empirical formula. We saw the empirical formula. So just quick revision. Okay, so 68% of data lies where? In first standard deviation. 65% values, we can say, deviation away from mean. Okay, then 95% values in second standard deviation away from mean, And lastly, 99.7%, it is in third standard deviation from me. Okay? Yes. Yes. The favorite hypothesis. The favorite question of the interviewer. Hypothesis testing. Okay. What is hypothesis? Hypothesis is educated guess about the population, or it is prediction between relationship between two or more variables. This is technical definition. What I'll tell you, let's see. I have made a product. Okay. I want to test it. I want to make few statements. Whether it will work, not on in all seasons. Another statement I'll make, not like this. It will not, how we can rephrase it? Just a minute. Whether it will, no, not whether. It will not work. Okay, more clear. And it will work in all seasons. In all seasons. Two statements. What is my expectation? My expectation is this. Yes, my product should work in all the seasons. Okay. So, who made these statements? Myself, because I have built this product. So that's the reason they have given educated guess. Because the one who has built product, he or she can make the guesses and have the test done for the real world. Okay. Tentative assumption about the population is made between two variables. Here we can say the two variables are this, A variable and B variable. It involves creating null hypothesis, default assumption, no effect, no difference, and alternate hypothesis which states there is a real effect. Okay. So, I made here two statements. What does null hypothesis say? It makes an assumption of no effect, no difference. First statement is my null hypothesis. Alternate hypothesis which state it is a real effect. This is the real effect. This is what I want and this is what I am going to test. Okay. So, data from random sample is analyzed using test statistic, and p-value is compared to significant value to determine enough evidence to reject null hypothesis or not to reject null hypothesis. Okay, so what I made statement, it will not work in all seasons. So what I'll do, I'll start finding evidences against it. So I will just check out whether it doesn't work in the festivals, in off seasons, or it is working daily. These are the evidence which I'll be getting. Okay, so let's say mobile phone. Mobile phone, is it seasonal? No, it is not. I have built the product as mobile phone. I will check whether it works in all seasons. It won't work in all seasons. Two statements, right? What I want it to work in all seasons. So I will start searching for the evidences that it will not work in all seasons. I'll start collecting the information. If I get evidence against, see, enough evidence to reject null hypothesis. If I don't get any evidence for this, if I don't get any evidence, then I will reject this statement. I will reject this statement. This statement is nothing but null hypothesis and accept the alternate hypothesis, the one which I wanted. In case I get some evidence for my null hypothesis, then I will fail to reject. I will fail to reject null hypothesis. Okay, and I will reject this alternate hypothesis. See, just now you might have observed I am not using the word except for null hypothesis. That's the reason is we don't want actually to accept the null hypothesis, right? We want to reject it only. So we say it, I fail to reject or I reject the null hypothesis. Fail to reject is indirectly accepted only. But I won't use the word accept related to null hypothesis. I will be using accept word with respect to the alternate hypothesis only. So that's the reason I use the word reject or fail to reject. This is the technical term which you need to use relating to null hypothesis or alternate hypothesis. Yes, you can say that I accept alternate hypothesis, but we can't say that I accept null hypothesis. Instead, we need to say fail to reject. Okay, these are the words. Just remember these terms because the interviewer sees all these things while explaining the hypothesis. Okay, so let's have a quick difference between null hypothesis and alternate hypothesis. Null hypothesis, it states that there is no relationship between two variables like this and this. Okay, alternate tells that there is a relationship between two variables. Let's say example, cancer patients are increasing due to the pollution. This is the alternate hypothesis. Null hypothesis, cancer patients are not increasing due to the pollution. Okay, then the investigator, the investigator tells exactly opposite of what he wants. Like, I am the investigator for this product and I have told it will not work in all seasons. Okay, it will not work in all seasons. I am telling exactly opposite of what I want. Alternate hypothesis says it will work in all seasons. The investigator says whatever or states the statements which he wants actually to be executed. Correct? Yes, we perform different statistical tests on hypothesis because we want the hypothesis to be either rejected or fail to reject. See, in case if we reject null hypothesis, by default alternate hypothesis is accepted. But if we fail to reject null hypothesis, alternate hypothesis is already rejected in that case. Correct? Okay. So procedure, just now I explained with the help of this product, phone product. Okay, that is the procedure of hypothesis. Okay, in hypothesis, how we decide about the to accept or reject null hypothesis? P-value is found. P-value is found. Okay, P-value is found and it is compared with alpha. Alpha value is mostly 99.9%, 0.05. Okay, this is the significance value. This is the significance value so that we can decide whether to accept or reject the null hypothesis. Okay, so what we do, we calculate this p-value. If p-value is less than 0.05, then null hypothesis is rejected. Okay, this is the practical way which I am telling you, which will be implemented in different models or in statistics for coding or for analysis purpose. Till now we have done the theoretical part. This is for the experiment. Okay, if p-value is greater than alpha, that is 0.05, we fail to reject null hypothesis. We fail to reject null hypothesis. Easy concept, just don't get confused. Whatever I have told you, just revise it. Easy to understand. Imagine that you are making a product and you want this product in the market in this way only. So what is the possibility of another statement that this product will have these whatever problems in the market. Just start finding evidences. If you find some evidence, then you accept it. If you don't find any evidence, then you reject the null hypothesis. Simple concept to understand. Okay. Yes. For doing the hypothesis testing, we have parametric test and non-parametric test. So we will be just having a look towards them, how different tests we can conduct for hypothesis test. See, actually this everything goes, from down to up. Like, I will be first conducting the test. Let's consider in this case U test, okay, or ANOVA test. Okay, if I get the value of P greater than or less than 0.05, then we come up and then we say, null hypothesis is rejected or fail to rejected. Clear? Okay, so it is actually from bottom to top, but mostly we see that like this tree diagram we see. Hypothesis, then it has two types: null hypothesis, alternate hypothesis. Some tests are conducted, statistical tests are conducted. Okay, which are those? Parametric, non-parametric, right? Whenever we see such diagrams, you will see such diagrams on internet and you will say, oh my god, this is such a big procedure. But trust me, actually while implementing, we go from bottom to top. Okay, so this is parametric. We have different tests here. Here you can see Z test, T test, F test, ANOVA test, etc. Okay, all these tests are there. Under non-parametric, we say H test, U test, chi-square test, etc. Okay, yes. So it is applied in population where population is normally distributed or assumed to be normal distributed. Okay, here population distribution is there, it's well and good. If it is not there, then we make some assumptions and we assume it as normally distributed. We make some changes and we assume that it is normally distributed. Parameters like mean, standard deviation is used here because see, normal distribution, what is the main criteria? Mean and deviation. Standard normal distribution, only the values change. Mean becomes 0 and deviation becomes 1. Okay, applied where data is quantitative. Okay, applied where data is quantitative. Quantity, okay, more powerful as they possess the ability to reject null hypothesis. While implementing in coding part, while analyzing, we'll come to know that they are more powerful. Okay, less robust. It uses mean as central tendency. Okay, yes. So let's start with the first t-test. Where it is used, t-test. It is the testing significance of difference of mean values. Sample size is small. Sample size is small, that is, it is less than 30 and population standard deviation is not known in this case. Where the population deviation is not known and sample size is also less, in that case t-test is performed. Okay, what all assumptions are made in this? Population distribution is normal, sample are random and independent, sample size is less, and population standard deviation is not known. Okay, population standard deviation is not known. Wherever the sample is less, population standard deviation is not known, there you can perform this t-test. Okay, they can be of two types: one sample t-test, two sample t-test. One sample t-test, here the sample mean is compared with the population mean. Okay, and here two sample t-test, two different sample means are conducted. Okay, so comparison, yes, I would like to tell whatever the test value we will getting in this t-test. Okay, so here we will be comparing it with the table value. We do have a table value for checking whether to accept or reject null hypothesis. This is also the one parameter. So if test statistic, okay, after performing this, we get test statistic value greater than table value. Remember, if we get test statistic value greater than table, then we reject null hypothesis. And in another case where it is less than the table value, what we will say? We fail to reject the null hypothesis. Yes, you said the statement correct. We fail to reject the null hypothesis. Okay. Z-test. It is, we can say, it also has the normal distribution. Okay, population distribution is normal. It is used to determine, when it is used to determine if population variance is known and sample size is greater than 30, is in larger number, means it is greater than 30. Okay, so the assumptions are population distribution is normal, samples are random and independent, sample size is larger, and population standard deviation is known in this case. Okay, they can be of same two types, one sample z-test and two sample z-test. One sample z-test, sample mean is compared with the population mean, and two sample z-test, two sample means are compared with each other. Okay, so when to use t-test and z-test? Okay, so t-test we are clear. Okay, we are already clear with the t-test. So if we see here the table, see, test static is greater than table value, reject. Okay, if sample size is less, population deviation not known or unknown, which test? T-test. Sample size is greater, okay, sample size is greater and population deviation known, in that case z-test. Clear with this, right? But what if sample size, can you guess which test will be applied here? Sample size is greater and population deviation unknown. Which test you would go with? Just think for a second, which test you would go? Yes, you would go with z-test, because any one parameter is there with us, like population standard deviation not known, it's okay, but sample size is large, yes, we can go. If one more question, sample size is less and population deviation known, which one? Same, z-test. Just now I told, right? Any one of them is known, then we can go with the z-test. Just try to remember this. Okay? Yes. ANOVA. ANOVA is analysis of variance. It was developed by Ronald Fisher, also known as Fisher's ANOVA. It is the extension of t-test and z-test. See, why it is called as, like, you can compare more than two samples in case of ANOVA. Okay, see, more than two samples can be compared. Okay, test significance of difference of mean values among more than two or more sample groups can be done. It assumes same population distribution is normal, samples are random and independent, homogeneity of sample variance, one-way ANOVA and two-way ANOVA. Okay, so same as the concepts of one-way, one test, one sample test or t-test and two sample t-test, same concepts. Okay, Yes, non-parametric test. Non-parametric test where population is not normally distributed, it is skewed. You remember we have done in the shape, skewness, kurtosis, right? We have covered these topics in descriptor stats. So yes, skewed distribution means either it is right skewed or it is left skewed. Okay, so such kind of distributions, it is applied where the distribution is squared, it is not normal distribution or assumed to be normal distribution. But most cases it is not assumed or it is very difficult. So in those cases where skewed distribution is there, we apply the non-parametric test. Okay, it is called distribution free test. It is often called distribution free test because normal distribution is not here. Okay, yes, mean and deviation is not used here. As it is skewed, we saw the skewness, mean, mode, median, all the three parameters change if the skewness is changed, right? So in that case, mean can't be used, so deviation can't be used. Yes, applied where qualitative, where data is qualitative, scale of measure either ordinal or nominal. You remember ordinal, we had done the order ranks, excellent, poor, right? Very good. These are the ranks, or first, second, third ranks, these are given. So this is ordinal. Nominal, just example of gender, male, female, or flowers, colors, etc. These are the nominal terms. It is more robust, less powerful. It uses median as the central tendency. It uses median. Can you recall where we use median as a central tendency? In this non-parametric test we use, but there is one more case where we use this median as central tendency. Can you just recall it? Yes, it is in categorical also. Categorical values also we do use median as central tendency. So test under non-parametric test are chi-square, U-test and H-test. Okay, let's start with chi-square test. It is used as goodness of fit. Means what? It determines whether your data significantly different from what you expected. Goodness of fit. Okay, it checks whether whatever data you are expecting, is it significantly different or it is not different. It depends. Test of independence of two categorical variables. Just now I told you it is also associated with categorical variables. So chi-square test is used for categorical variables also. Okay, yes, makes comparison between expected and observed frequency. It whatever the expectations we have, it compares it with the observed frequencies. Okay, so we can say the difference between the actual and the predicted. Okay, greater the difference, greater the value of chi-square. Greater is the difference, greater is the value of chi-square. If there is no difference between expected and the observed, then the value of chi-square is 0. Okay, so what is the conditions for this chi-square test? Observations recorded, used or collected on random basis. These all are done random basis. The first topic today we covered was random variable, right? Random sample, that is also randomly which we take, correct? All items in sample must be independent. No group should contain very few items less than 10. If the value is below 10, then this test cannot be conducted. So it should be more than 10. Or overall number of items must be reasonably large. It should be normally at least 50. It should be at least 50. These are few conditions under which chi-square test can be conducted. Okay. U-test. U-test, it is used to investigate where two independent samples were selected from population having having same distributions. Okay, independent variables. This is variable 1 and this is variable 2. These are the two different samples independent samples were collected from population having same distribution. If this is having normal, this will also have normal. If it is having skew, this will also have skew. So the distribution should be same for the random samples here. Gives most accurate estimate of significance, especially when sample size are small and population is not distributed normally. See, these tests, whatever we are doing, those already come under non-parametric test, correct? So here the population is not normally distributed, that we are sure about that, right? But U test, it is applied where the sample size is small. Okay, sample size is small and population is not normally distributed. It is used for continuous or ordinal data. Excellent, poor, average, wherever these, I'm just telling you the examples where these are in the data set, there U test can be applied. Okay, I would like to tell you one interesting thing. Whenever we do comparison between two categorical columns, at the back end in ML of the functions, we have different libraries, different functions in machine learning. Okay, so at the back end, the whole statics is applied. So calculating two continuous columns, for example, average speed, and we can say average speed and average distance. Okay, so these two are continuous values. So this, to compare or to execute, to test, to conduct a test, we can use the U test here. Okay, so the example we just discussed is average speed with distance. Yes, we can say like this. Okay, it is also known as Mann-Whitney-Whitson test, Mann-Whitney-Whitson rank sum test. Okay, H test. It is used for comparing two or more independent samples of different or equal sample sizes. Okay, see what U test said right now to us, whether two independent samples are selected, that are selected from population having same distributions. Okay, to investigate, to work on these two samples. What does H test tells us? Compare two or more independent samples of equal or different sample sizes. See, it extends U test. That's why I went back, showed you the slide again, U test, and again I'm giving you the analogy with it. The H test is used for comparing only two groups. Okay, but here it is more than two groups. One-way ANOVA test is the parametric equivalent of this. You remember in ANOVA, the T test and Z test, right? They both have one or two samples, right? But ANOVA, it can have more than two samples. The same analogy you can have with H test. U test has two groups, H test can have more than two groups. Okay, so that's why it is the parametric equivalent of this test, ANOVA. Also, it is called one-way ANOVA on ranks. Okay, it uses instead of ranks instead of actual. How does it work? I'll tell you. See, let's suppose column 1 in our data set. This is our data set. Not column 1, I'll write height. I'll write here weight. Okay, so what it does, suppose height is 163 and weight is 45. Then height is, I'll just take some few data points here. Just don't make a relation between height and weight. I'm just writing the numbers just to explain you. 175 and it will be 46. Okay, so instead of using, this is our actual data, correct? Instead of using this actual data, it will give ranks to it. 0 is not a rank. 1, 2, 3, 4, 5, 6. So it will be using the ranks in this way. Okay, doesn't assume the population to be normally distributed, which we already accepted while going through non-parametric test. Okay, so We have done so many tests today. We saw the distributions. We did all these things. But in real time, if you want to launch a product in the market, we need to do the A/B testing. What is A/B testing? Let's take the previous example of my mobile phone. I have launched a phone in the market. I want to launch it. So what I'm doing, I'm making two types of advertise. Okay, I'm doing two types of advertisements. This is A and this is B. I will launch both of them. I'll go print the posters. I'll just put it on Google, YouTube, everything. Then I will make a research, an analysis. Which one of them is giving me more likes, more views? Correct? So let's suppose A is the original, okay, original advertisement or original poster, okay. B, I have made some changes and I have launched it in the market. So I am getting more views, more clicks for B. Then what I'll do? I'll be going with the B one, B advertise or B click, correct? B posters, and then so that I'll get more and more sale for the product. Okay, so let's have the definition here. Way to compare two versions of a variable to find which performs better in controlled environment. See, the environment is the actual environment, that is the real world, and which of these two versions, whether A or B, we are talking, which one is the better one to have the product launch. Okay, how it takes place, just now I told you the procedure. Divide a product in two parts, A and B, see which one gets more clicks or sold. Okay, it allows decision maker to choose the best design for a website by looking at the analytics. See, sometimes while searching any costumes on Flipkart, okay, so you just select a product which you like and you want to view more different products of the same company. So in that case, that product will be getting more and more likes. So the first poster, or let's say the first image which that company had launched, it is getting more likes. So they will be continuing and going with the same product only, the same image or the same poster or the same link. Okay, we can consider. This is done by having the analytics results obtained with two possible alternatives, A and B. Whatever we have just done with our product, mobile product, A and B. A is as it is, I have not done changes, just launching, okay, this is my mobile phone, please have a look, please purchase it. B will be having some attractive advertisements, attractive features, attractive posters and attractive some logos to advertise my product. Okay, so how we do this testing? Define the goal, what the goal you want to set. Create variants. In my case it is A, B. In your case it will be C, D, whichever you want. Make the changes accordingly. Split your audience. Now suppose this is my product. I want to give my product only in one area. Let's suppose I will give this in Pune. I'll give this in Mumbai. Correct. Then I will, A is in Pune and B product or whatever. If it is physical, then it will be in Mumbai. And if it is not physical, it is online, then it will be open for all. Okay. So randomly split your audience. You can go and give physical posters also to the public. So this comes under this criteria. Run the test. Start. Suppose today I have just distributed. Wait, see how the response is going on. Analyze the result. Here, while running the test, note it down. Which users which one they are liking, the A or B part. Okay, so which one they are liking, the A variant or the B variant, and then you make the analysis of those results and then implement whichever the winner is there. In my case, B was the winner, so I will be launching the product with B solution with B variant. Okay, so today's just a small recap. We went through the inferential statistics. In inferential statistics, we saw importance of inferential statistics, random variable, estimate, then hypothesis testing. We saw different distributions, probability distribution functions, discrete, continuous. Under discrete, we saw uniform, then binomial, Bernoulli. Okay, all these things we saw. Later on in continuous, we saw normal, standard normal distribution, and then chi-square distribution. Later on, we went to hypothesis testing. To understand or to predict about the outcome, we check out the hypothesis. Hypothesis, null hypothesis, alternate hypothesis. Null hypothesis, what it does, it is the statement which the investigator doesn't want to be true. And alternate hypothesis is in the favor of investigators. You can remember in this way. So, we use the sentence in the following manner. We reject the null hypothesis or we fail to reject the null hypothesis. We accept alternate hypothesis, we reject alternate hypothesis. So just remember these important words and sentences. Later on, we just had a quick look at the different parametric and non-parametric test, chi-square test, U test, T test, ANOVA, etc. Okay, and finally, we just understood how to have the A/B testing and what is the importance of A/B testing. I'll just give you a look of the code. Okay, I'll just give you the look of the code. So how these tests can be viewed on a data set. I've just randomly took a data set. So this is student activity data set. Okay, so weight of the students, okay, bus arrival time, then studies hours per day, website clicks per day, how the student clicks, then monthly pocket money. So many parameters are there. So we will just have the uniform distribution of this. See, can you see this is the uniform distribution? Alright. So almost all of them are having equally likely like probability, right? Events we discussed already. Binomial, what is the binomial? It will have outcome, pass, fail, success, failure. Okay, then it will have a number of experiments conducted, right? Just revising the concepts also. So see, this is binomial distribution. This is binomial distribution. Bernoulli distribution. It will have only one outcome. Two outcomes, right? Sorry. Pass, fail, tossing of a coin, heads, tails, etc. See, Bernoulli, it will give only two. Okay. I have just plotted this on basis of different columns. You can see with different columns also. Okay, you can also go through it. So this is Poisson distribution. See, what is Poisson distribution? Here the outcome of the event is very less, but the experiments conducted randomly have a very high value, that is n. So in that case, Poisson distribution. See, website clicks per day. Okay, like this. Normal distribution. This is normal distribution, exam scores. So we can see, as I discussed, we have maximum data between 95 confidence interval. See, maximum data here. We can say it is from 40 to 100. Yes, correct. Okay, this is log normal distribution. T distribution. This is T distribution. chi-square distribution. See, chi-square distribution we already saw. It is not normally distributed. So here you can see it is skewed, right skew, correct? Yes, this is our standard normal distribution. See, 0, 1, 2, 3, minus 1, 2, minus 2, minus 3. We will see here normal distribution. See, normal distribution 70, 80, 90, 100, 60, 50, 40. Clear? Got a clear visualization and actual visualization, right? Okay, so these were the different different distributions under inferential statistics. So in 2 sessions, we saw the importance of statics, the hidden power of statics, descriptive and inferential. We came to know how it is important in machine learning and data science. We run through all the concepts of descriptive and inferential. So thank you guys for watching this video. Stay tuned for more educational videos. Thank you.